My name is Brian Herrera.
I'm Verley.
And I'm Jaden, and this is lab number 9.
First, we had to calibrate the interferometer. We did this by calculating a wavelength by looking at the difference of the micrometer movement versus the number of fringes that passed and comparing it to a known wavelength in order to get a scaling factor to use for the rest of the lab. And then we measured wavelengths of two different light sources. First, we used the green mercury light source and found an average wavelength of 544.99 nanometers, which had a percent error of 0.2%, but our standard deviation amongst our measurements was 36 nanometers, which was bad, which came from challenges with actually counting the fringe spacings. Next, we used the yellow sodium light source, and we found a wavelength of 582 nanometers with a percent error of 1.2% and a smaller standard deviation at 12 nanometers. The percent error difference in doing one additional fringe count by accident for 50 fringes came out to 1.961%, and one less fringe than necessary came out to 2.041%.
The yellow sodium source has two separate wavelengths that are really close together. This causes two separate intensities and two Haydinger fringes patterns. So by moving in large separations of D, you can see that there are no fringes in certain areas. We measured 3 of these null fringes to find a separation of 0.597 nanometers with a percent error of 0.05%. This was our total intensity equation.
The total intensity was derived using clever trigonometric tricks.
In this portion of the experiment, we used the interferometer with this vacuum chamber and added it to the normal setup and slowly pumped out air to move the fringe pattern. This effectively changed the optical path distance of the system, and so when we pumped air out, fringes moved on the screen. So using this equation right here, we were able to count the separation in fringes and the separation of pressure, and ultimately we get a change in refractive index that comes from pumping air out of the chamber. We're able to get a slope here, and since we know that the refractive index of vacuum is 1, where pressure is 0, we can plot something, which I'll show. You can see that relationship here where 0 pressure starts at 1, and then we go up with a slope of about 1 times 10 to the or 2 times 2.7 times 10 to the negative 6th. And you can see that gives us a refractive index of about 1.0002. So we compared our result with 3 zeros, 0.21, with the ideal result of 1.00027, and that result comes from an adjustment from temperature after comparing at 0 Celsius. So between Mount Lemmon and Tucson, there's about 140 millimeter of mercury change, and that would create 214 fringes with our fit.